Oh, man. Quick review of the two tricks that I taught you yesterday, Friday. Trick number one, take a pattern, increasing by 20, for example, every cell, and you got to highlight both of them. That's the difference between this one and that one. The one on the right, you just highlight the one. This one, you got to show them the pattern. So the pattern is increasing by 20 every time. So you simply drag the two blocks thing down to where you think it might be. If you miss it, you can always adjust it, and we get 6 hours worth of minutes, which is 360. That's a pattern. This one's a formula, and we showed the universal symbol for formula was an equal sign, and then we wanted to reference the cell above it, so we click on that. And then what do we do instead of an X for multiplying? The asterisk, the star, which is Shift 8, and we want to multiply it by 2. And so that's not just a formula for this cell, it's a formula any place you put it is going to reference the cell above it. So we can just drag it down. Maybe. Do that right? No. Drag it down. And we've got our 262,000, more than 250,000 bacteria in 6 hours. And we said that was a very specific type of growth. Called what? Called exponential growth. Good. So, exponential growth. Is that rain? You hear that? Or is that just the air system? Okay. Exponential growth is basically, well, what noise does that graph make? What noise does that graph make? Right? That's hard with the mask. That's the noise that graph makes. If you had to pick a letter of the alphabet, what letter would that graph be? All right. You guys, J. We're absent that day in kindergarten. Yes, it's a J. It's a J. Good. What we know is that exponential growth is what happens every time a population has unlimited resources, has all the stuff it needs, has ideal conditions. Basically, what happens when they have everything they need is they start to reproduce at a constant rate. And when anything reproduces at a constant rate, they begin to have a doubling time, as in every 20 minutes for those bacteria, or every 30 years for humans. It's a period, a regular interval at which the population doubles. And as soon as you have that, you have an exponential growth curve. Like Grant said, it's a J curve. But something should bother you about that stuff you just wrote. Something you just wrote shouldn't sound quite right. What did you just write that's not real? Aren't resources kind of, by definition, finite? Right? Resource is something that can be used up, right? So what we know about exponential growth is this: it cannot continue forever. Something runs out. Something, and by the way, we call the thing that runs out first. Well, do you remember? I mentioned it when we were talking about the nitrogen cycle, because for a lot of plants, it turns out to be nitrogen. Good. We call it in general the limiting factor, and when it's an element, we call it the limiting nutrient. Absolutely. Yeah.
So is the sun not considered an resource?
I mean, it's going to run out at some point, isn't it? And there's a maximum amount of energy you can get from sunlight, isn't there? Like you're right. You pick the one that is like the least limited, but it is still limited. Like if you put a solar panel up, it's not that the sun will run out. It's that there's only so much energy you can get that solar panel to turn that sun into. And if you keep putting loads on that electricity, eventually you won't be able to add any more.
What about air?
What about air?
Like, isn't that?
Is it? If I keep using up the oxygen in the atmosphere and nothing regenerates it, I cut down all the trees that regenerate oxygen, doesn't it run out eventually? Again, you're picking great examples of things that we think of as unlimited, but they can totally be used up. So something's got to give, right? And so we are going to see a shift anytime there's exponential growth. Okay. Go back to your graph. And I want you to make a new sheet. Do you know how to do that? So you go down to the bottom. And you see that you should have a sheet 1. In fact, go ahead and tap on sheet 1. Or maybe it's double tap on sheet 1 and rename it exponential. And make a new sheet by clicking on the plus sign in the lower left for add sheet. And that'll give you another sheet that it'll probably call sheet 2. And in that sheet, I would like you to enter this data. Now, you can use the trick on the left-hand column. Put a 0 and a 10 in, highlight them both, drag it down. That trick will work just fine there. You will not be able to use any tricks in the right-hand column. The right-hand column, you'll have to actually enter the data in. So, do that and then graph it. Remember, highlight both columns. And then what do they call, what tab do you go to make a graph? Insert, and they don't call it a graph, they call it a chart. Good, chart. Graph now. Good. So every graph tells a story. What story does this graph tell you about these fruit flies? You know what fruit flies are? Like they show up in your kitchen if you got like bananas hanging out. That's one of their favorites. Little tiny, little tiny little gnat-like things. What's going on with these fruit flies? What's the story?
They bred a bunch, but then they ran out of resources.
They bred a bunch, and then they must have run into their limiting nutrient, right? Whatever it was. What do you think? Give me some things that could have been a limiting factor. What situation could have caused these fruit flies to stop growing? Sure, maybe it was winter. Maybe they ran out of bananas. Yeah. What else?
Forest fire.
Sure, a forest fire. But it doesn't matter. Something gave, right? Something ran out. Although it sure looks like there's more to the story. What happens at the end? Are they just flatlined? Steady population? What's going on? They're kind of bouncing, aren't they? They're kind of bouncing up and down. Okay, so we have a name for that one too. Any Matthew people know the name? We started with exponential. What's this one called? All right. Logistic. And we have a name for that line that they're bouncing around too. And that line is called the carrying capacity. Go ahead and draw that in your notes. Okay, alphabet. Pick a letter for this one. Oh, good. Good job. That's an S curve. J curve, S curve. All right. So logistic growth, you noticed it started as exponential growth. There was a doubling time. But then things changed. Something ran out. No more bananas. Or maybe there were so many fruit flies that a spider moved in and built the web. And suddenly, some of those fruit flies were being caught and eaten every day. Doesn't matter. They ran into something that limited their population. And we call this an S curve, and we call the dotted line, that ceiling that they top out at, we call that the carrying capacity.
So would the carrying capacity on that last chart be 495 or 510? It starts to level.
Great question, because realistic logistic growth tends to bounce. Then where is the actual carrying capacity? We generally say it's in the middle of that bounce. You know, they're overshooting it and they're undershooting it, and draw that middle, and that's typically the line. Good question. Good way to describe logistic growth is this is exponential growth after reality has set in. It's probably also worth drawing what a real life logistic curve looks like. Which is to say, let's say we're talking about these fruit flies and they're living in this kitchen and there's this finite amount of fruit and they're getting to the point where there's too many of them. Do they look at each other and say, oh dear, we appear to be approaching our carrying capacity. Perhaps we should stop reproducing. Do they do that? No, they're fruit flies. Same with rabbits. Same with pretty much every population we've ever seen. What they do instead is they overshoot, and then there's a crash, right? There's this segment right here, which is just a downward slope and a graph, but in real life, that's a bunch of dead fruit flies, right? That's the fruit flies starved or got eaten or whatever that limiting factor was. And then they undershot the carrying capacity, and we're still reproducing, so then there's more, and they overshoot again. Real life carrying capacity tends to get bounced around, right? Real life logistic growth tends to have little crashes once they overshoot carrying capacity. Any more questions? You've asked some good ones today. I like that you're already thinking about, what are limited resources? Like, can I think of some that aren't? That's awesome. That bleeds into chapter 6 pretty well.
How long would it take for the ocean to evaporate?
Ooh, how long would it take for the ocean to evaporate? I suppose that depends on cloud cover and
It's sunny all the time with no rain.
yeah, I don't know. That would be a really interesting math problem. How much water is there? How much surface area? What's the rate of evaporation in full sun? Love it. And then at what point does the air get so saturated with that water that it's just going to rain back down? Good. That's good for a Monday. Let's do a guided reading. Do Wednesday, and that'll be it. What we got? 10 minutes. 10 minutes to work. Stop.